Hello everybody, today I want to demonstrate you how to derive the mass conservation equation using this volume element. And you will see it's very simple and straightforward, and the mathematics behind is more than simple. What does mass conservation mean? Mass conservation mean, if I just redraw this volume element here again, what it means that we have this relation, everybody knows it. We keep the volume constant, so the volume is constant here, and now the first assumption, if we say the density is also constant, that means the mass inside is constant, it is not changing. And if we put, so if this is 1 meter, 1 meter, 1 meter, so we get 1 cubic meter, let's say, of water, and we take we have here another cube with 0.1 meter, and 0.1, that is complete filled with water, and we just want to put it in. What will happen? The whole volume of this will go out somewhere. So if you put it in, the same amount has to go out. This is mass conservation. Mass has to be balanced. Everything what is going in has to go out. So this would be the first thing. And if we consider that the density is not constant and we heat the volume up somehow and we change density, for example, that the density will getting higher, also the mass is getting higher if you keep the volume constant. So, and to do this, due to the fact that we have here a special amount of mass inside, mass should enter through the phase to compensate this. So finally mass has to be conserved. The first thing was everything was going in is going out, and here the mass has to be conserved due to that. And we will derive now the mass conservation equation. For that, if you are not so familiar with all the stuff, just imagine that we have here some water soil, and the height is h, and for you we put this volume element somewhere here inside. Due to the gravity, which is directed downward, the fluid, if you assume the water column here, then the water will accelerate downward. We will get some velocity x direction here if we introduce a coordinate system like this here. And what will we expect? We will expect that the water will accelerate, will going down, and it will flowing through this control volume element. So here it will pass through this phase and will leave the volume element at this phase or at some other phases. And to make things more clearer, what we need, the mathematic point of view, so we have here control volume plane, some area, and we want to know how much water is going through. So finally it's the mass flux or volumetric flux, and we will denote it by phi, and it has the units kilogram per second or cubic meter per second. And in OpenFOAM this is denoted by phi. If you go to the create header .h file, so to the header file, you will see that fierce surface scalar field. We have here some surface, and yeah, the value of the mass flux or volumetric flux is a scalar. So you see here you can derive it directly. And what we have in addition, it's also velocity in x. So these are the same. And if we are interested in how much water is going through this red marked area, we just calculate it. Vm is representing the mass flux, and this is the density multiplied the area multiplied the velocity in x direction. So if you don't believe me that this is the mass flux, you simply can check the units. It's kilogram per cubic meter, it's square meter, and of course it's meter per second. We get rid of the cubic meter because here we have square meter, meter, cubic meter. This will cancel out and we end up with kilogram per seconds. Yeah, so what we learned, believe me. And the volumetric flux is simply the mass flux divided by the density, and we end up with the area and ux. Yeah, and I will demonstrate that the units are fine. So what do we need for the further investigation? We need to know this one, how to calculate the mass flux in some area or on some area. So this was just for the beginning, and now things get easy and clear, so I think everybody can follow me. I will derive the mass conservation equation only in more detail in the x direction. So we have these two faces, so just think about the river here. Flow is entering this side and is going out on this side or wherever. But if we are just looking to the x direction, yeah, it's like this. What we know here is we have the points. Because these are fixed points, we have the coordinates. And if we know the coordinates, we also know the distance in between. And this, of course, I think everybody agree that this is delta y, corresponding to this coordinate system. What else we know? We know that the velocity vector in x has to be perpendicular to the face, and we have some density here. And we know the same, we have here some velocity in x direction and some density. And now we have to introduce a very important mathematic description. So what can happen? Imagine that there is another cell and then there is a wall, like here. And the flow is going on x direction and it's forced to go up. So that means the flow can go in this direction. What does this mean to the components of ux here and ux here? They do not have to be the same. Yeah, they can change. The same is with the density. Just imagine we have here density or a fixed temperature or a uniform temperature where we enter at the red phase. In the volume itself we introduce some energy, it will heat it up, and then the density here at the green phase would be different. And yeah, therefore we mark this that we are talking about the density at the green phase here, and this is at position x plus delta x. I will demonstrate why this is x plus delta x. because we can introduce that this point here is x, and if this point is x, this point is simply x plus the distance delta x. So this is the mathematical expression that we are talking about density and velocity at this phase. And yeah, if we are talking about the red phase here, we simply say it's at the point x. So if I say point x, it's really always corresponding to the red, to the phase. If I say at the point x plus delta x, it's corresponding to the green phase. So, and now we can simply say the mass flux, what is going in x direction. Yeah, what is it? It is the area, the red area. It's delta z, delta y, multiplied the density and the velocity in x direction at, I will mark it with the color, at the position x. So we are talking about the values at the red phase, and we can do the same in x direction of the flux which is leaving. We have the same area and we have the velocity in x and the density, but now we are interested in the values of position x plus delta x, or at the green phase. So finally what we have to do, we have to make a balance, and this is, we just subtract what's going in and what's going out. So phi in x direction is delta z, delta y, and now I just put out the area. This should be clear for everybody. Now I will mark it the last time and I subtract it. So it's plus delta x. This line is finally this here. We don't need this anymore. Yeah, and you can do the same for y and z, and I will write it direct. So in y direction we have x multiplied z, and density in y, density and y plus delta y. You can, if you don't trust me, please do it yourself. I highly recommend that you will derive it yourself if you're interested in that stuff, because then you really understand what's going up, due to the fact that you are dealing with these equations, you are dealing with the mathematics behind, and yeah, then you get familiar with that. Or you're really a very intelligent person, but I'm not the intelligent person, so I have to derive it every day once, otherwise I will forget it. Yeah, and this here is the flux which is going in and out in x direction, y direction and z direction. So that finally it's the balance, and the balance, so this is surface mass which is entering surface. The surface is always here. It's an area. So yeah, and the flux which will cross this area, I will say this is the surface, it's a phenomena. You also could say it's the first phenomena due to velocity. I'm not sure if you can say it's a phenomena, but I will just introduce it now. Because the mass which is going in and out, it's due to the velocity. If there is no velocity, mass would not enter the surface or leaving the surface. But the velocity is finally due to some force. So just remember the bed and the flow which is going down. This flow is only going down due to the gravitational force G. If this would be zero, yeah, the water will not go downstream. And the second phenomena is due to compression and expansion. Yeah, and compression and expansion, this is time dependent stuff, so we have here space. Compression and expansion is always related to density change. If you think about water, if you cool it or heat it up, you also have density change, and this is also some expansion or compression. But yeah, it's something else if we have air and we compress or expand this, but it's the same phenomena behind. And density change is in time. That means we have here the timeline and here the density. We have, for example, we have here T is 1 and T is 2. We have two different densities. Density 2 and density 1. And the function could look somehow else. And we have here this, so we get here in between delta t, and we get here delta rho. Yeah, this we can define as the change of density during time, and this acts on a volume. If you are not sure about where it acts on, you just have to check out the units. So this acts on some volume, so the density is some volume guy. So then we have this. So this would be the first phenomena. The second one would be compression and expansion, and this is simply delta rho delta t multiplied by the, as I told, by the volume of the control volume, and this is simply delta x delta y delta z. And of course compression and expansion also, we have this time derivative, but we'll also change the density inside our convective terms, or flux terms. We don't need this anymore, and we will sum up everything, so we have everything together. And if we want to get the point what is changing inside, so mass flux which is changing inside, we have just to sum up. That means so we already talked about, due to the flow, a mass is going in or out, and due to, and now we think about there's no flow, but we have different rho 1 and rho 0 and rho 1. What will happen? They are, I will say, not equal. Yeah, so one of them is higher than the other one, and if we fix here the points, and these are membranes, so what will happen if we get shrinkage, and the membranes will look like this. If we get not shrinkage, it will look like that, and flux is either going in or going out to compensate the mass change inside. So again, mass has to be conserved, and that's why I will write it in that way. This has to be equal to density ux at position x, density ux at the position x plus delta x, plus x multiplied z density uy at the position y. So if you really derive it by yourself, the only thing what you have to be careful is to be concentrated, that you do not mix up any terms or signs, and then you really see that it's very easy. I think if you watch this video, you will now at the moment you really realize that there is no black magic behind, so everything is very easy. So, and what we are doing now, we multiply the whole equation by 1 over delta x, delta y, and delta z. This is finally the volume of our control volume element, and we do not need this anymore. So we end up with the following. Oh no, here we don't have partial guys yet, but soon. T is equal to density velocity in x direction at phase of position x, density velocity in x direction, x plus delta x, and we have to divide this by delta x, and then we have the next term that expresses the fluxes that are going inside and outside in y direction. We have to divide this by delta y. I really hope that I make no mistakes, but as far as I have the feeling at the moment, I will not do it, so just relax. But I think you already know what I will write, so because it's always the same, nothing special. So yeah, just to make it complete, multiplied by the volume, everything is vanishing. Multiplied by the volume, we end up with 1 over delta x is remaining. Here 1 over delta y, and here 1 over delta z. So this is, everything is fine here. So the next thing what I will talk about is about this term here on top. I will rewrite it, it's ux position x minus ux at the position x plus delta x. So we also can make the brackets here, doesn't matter. So what is this representing? If I don't know what it will represent, then I will always make some small draft that will really demonstrate what it will be. So I will imagine that I have here this value at the position x. That means that here we have position x, and somewhere here we will have density ux at the position x plus delta x. Yeah, and what does that mean? We have here the position x plus dx. That means this one would be dx, and this one would be delta rho ux. Yeah, I think this is clear. We just subtract this minus this. And then, yeah, we end up that delta rho ux is finally rho ux at the position x plus delta x minus rho ux at the position x. So, and if I will rewrite this again to make things so simple, it's equal to, I will write this one, it's a minus, and this one I will write b. So, and when this one is b minus, yeah, and this is a. So here it's direct vice versa. We have here it's like b minus a. So you see what it is? It's finally it's the minus sign. What is the difference here? So now you know where the minus sign come from, and this was, yeah, the reason why I did it so clear. So you see that this is similar, and this is finally this one. So I will rewrite this equation in a more readable form, and this delta ux divided by delta x plus minus delta density y divided by y plus minus delta rho u z divided by delta z. So yeah, you really know why I wrote it in that way. And now what we have to introduce, or we will not introduce something, but now we take this point and we put it here, put it here, put it here, we put it here, and we make delta x going to 0. So finally delta will go to 0. And for x, y, and z. So what we, in the mathematical expression, we use the Linus of delta, I will write it nicer, delta x. When delta is going to 0, it will change into the partial symbol. And that's the magic. the same is valid for so yeah, it's like if delta x going, you also can say delta x and delta t is going to 0, we end up with partial signs. So if you are not so familiar, simply replace delta by partial sign. And that is how mathematics works. No. So you know what I'm doing now, I will replace everything here due to the fact that I will make my volume element smaller and smaller and smaller and smaller. And then we will end up with this equation rho u x minus rho u y not plus minus density u and z divided by z. So, and here we go, this is the mass conservation equation. To make things clearer, I just push the right hand side to the left hand side, and we will up with exactly the same, but now this equation you really can find in most literatures, and you will find this equation in all literatures about fluid dynamics. And this has to be 0. Yeah, so now we get the mass conservation equation. It's here. You saw it's very easy and straightforward. No black magic, no difficult mathematics behind. And I just want to introduce the Nabla operator. That is simply, or it simply contains the 3 derivatives in space of x, y and z. And I introduced the velocity vector that has the components in x, in y and in z direction. People also write here the vector signs, but if we are talking about fluid dynamics, it's clear that it's a vector, and it's clear that which components it contains. So it's maybe in a mathematic point of view we should write it, but if we are talking about fluid dynamics, it's clear. And then we can rewrite this equation into a vector form, and this is simply plus the big bullet is the divergence operator. This one is divergence of rho u, and about the operators I will talk in a different lecture. And I will also talk about tensors and scalars and vectors, which are actually also tensors of 0 and first rank. And I will also talk about second rank tensors and mathematical operators. And yeah, here we go. This is the mass conservation equation in Cartesian coordinates. This is the mass conservation equation in vector form. We also use this in OpenFOAM, and we also can rewrite this in integral form So this would be density and would be integrated by the volume plus surface integral of rho u. N is the surface normal vector, is equal to 0. So this would be at last the vector form of the mass conservation equation. So I think we are done. I hope you get the point how to derive this equation. In my opinion, it's not really difficult, and if you know how to derive this mass conservation equation, you also can derive the momentum equation in a similar way. The only difference is that we get rid of this is equal to 0, we get some sources here, and then finally it's the same. So thanks for watching. I hope I could solve some problems, and if you want to know special topics, just let me know. And yeah, I wish you good evening, see you soon, and keep foaming. Bye.